So I think I will be the most experimental presentation of this workshop. In fact, I will show no models, no equation. I will just show some experimental boundary conditions. That's all. The talk I will present you is just a discussion about the choice of the boundary condition. Testing machines start at the early 18th century, and from that time there was a slow evolution of the boundary condition for the study of standard continuum mechanics. So this is what I call standard continuum experimental mechanics. This is all the solutions that were developed for that. And now, for a few decades, the study of generalized continuum mechanics starts. And so the question is, do we have to keep the same type of boundary condition, or can we change them? Is it interesting to change them or not? I won't say that I have the answer to this question, but at least I would like to raise this question. So it will be a sort of short review of the different static tests. So I won't focus on dynamic ones, which also exist and are really interesting, but this is not the purpose here.
What it means, AKA?
Oh, also known as. Oh yeah, that's bad. Sorry. First I will make a very short introduction considering full field measurement based identification methods that are the modern way to identify different material parameters. They are really important nowadays, so it's important for me and for you to be aware of that. And then I will focus on the boundary condition, because the choice of the boundary condition of course depends on the type of measurement you use. So I will first focus on that, and then I will describe the different type of boundary conditions that were used and are still used for standard continuum mechanics. And then I will describe the different type, but not all of them, because I'm not a genius. I can just have some ideas of what exists, but I can't read everything. But the different type of boundary condition you can find for generalized continuum mechanics. And then I will have a short summary. So we are currently with a growing experimental approach that is a mix of full field kinematic measurements with numerical inverse problem methods. This started in the early 80s, because at that time you've got several technical and scientific evolution, and different methods for both the measurement and for the inverse numerical inverse problem were proposed. At the same time, you've got moire, you've got grid, you've got digital image correlation, and even more that are possible. And different methods for the numerical inverse problem could be like virtual field method, equilibrium gap method, constitutive equation gap method, and probably the most famous one, and in the spirit perhaps the most simple one, the finite element method update, which is, if you are not aware of it, just the fact that you will update the parameters of your finite element simulation so that you can make your numerical results converge towards your measurements. And so if the convergence is good, you can guess that your material parameters of your finite element model are okay. You've got a very interesting review of all this identification method in this paper of Avril et al. In 2008, if you are interested in that. Why is it working? Well, it's working and it's spreading in a very fast way, because first it replaces the previous methods. You can do exactly what you were doing before, but with full field measurement, with more robustness and all of that. But also it enables new type of identifications that are field related. You can study localized phenomenon. You can identify non-local model, for example. You can identify things like patterns, like for example in thermal fatigue, where cracks appears with different specific patterns. It is also interesting because it takes into account different experimental, XP is for experimental, it takes into account different experimental defects, like for example the shape of your specimen. If it's not perfectly the shape, the nominal shape you expect, perhaps with the camera you can see that it's a little bit different. It can measure the boundary condition displacement. This could be interesting. You're supposed to be fixed, but well, in fact, the stiffness is not that high, and you've got a small motion. You can measure it with a full field measurement. It's also rather easy from a technical point of view. That is to say, you've got small modification to do. If you have a prior test, you just take off the strain gauge, I would say, and apply a speckle, a grid, circles, whatever you want, and a camera. So it's not very complex from a technical point of view. After the post-processing is more complex, but at least the measurement in itself is not. And last but not least, the necessary technologies are at hand. I mean, all these methods, this combination of numerical inverse method and digital measurement were developed since the beginning of the 80s, because at that time you start to have cheap visible digital cameras, you start to have cheap computing power, you start to have cheap memory storage, okay? At least from an economical point of view, not from an ecological one, but at least the cost is small for us. And last but not least, I would say it's purely commercial, but I would say it goes really done very well. I mean, if you are in a presentation and you are showing images that are moving like this one, everyone seems to be interested. It's much better than just a number. I mean, it's not scientific, I mean, but at least you say, well, this seems to be really good just because of the image. I can say that because this is one of my tests. This is a crack that we orient during the test, and without full field measurement it's impossible, clearly. And the result is like, wow, it's just a wow effect. Are there limitations to this new approach? Well, virtually no, I would say. As long as one thing, the thought behavior is induced. I mean, you tackle the parameter you want to identify.
So you are not measuring forces.
Oh, with that you're not measuring forces. This is a problem, usually, yes.
It's not a problem. Forces are not existing.
Oh, yeah. That's a good discussion. Yes, you're measuring displacement, and usually this is a real problem, because usually you will measure forces in a very poor way. You will have just one scalar and a full field measurement of the kinematic. So this is a very important contrast, and this could lead to some problems. What you must remember is that the displacement field you are measuring is a response to a given stimulus. This is the most important thing. I mean, everyone in this room is aware of that, of course, but sometimes we forget that, because now we've got this beautiful full field measurement. So boundary conditions are still mandatory. We need them. We need to choose them. But they are not as popular as what I said before, because, well, it's just out of the gauge zone. I mean, you do not see them, you do not show them, because you are measuring the full field measurement on the gauge zone, and it's just outside, so you do not see them. It has really a 19th century look. I mean, it's just bolts and bulky steel parts. It's not beautiful modern technologies usually. It's usually not well known, and I mean the information is not well transmitted inside a team. I mean, usually the guy who knows exactly the boundary condition, well, it's a technician. It's perhaps the engineer that performs the test, the PhD. But the researcher, well, knows the model, but perhaps has not done the test himself. And what is important is, when you perform the test, to know what is the implication of a small change of the boundary condition on your model identification. And because sometimes it's not the same person that do all the identification, you lose some information. And last but not least, often it's very limited because of technology. I mean, you cannot do whatever you want in terms of boundary condition.
In France, you have technicians.
Less and less. Usually,
This problem we don't have.
I'm looking for myself, and I'm looking for my own tools and boards. So my talks concern boundary condition because usually we forget to speak about that. So, what has been done concerning standard continuum mechanics? The first idea that emerged at the very beginning of, 18th century, just a little bit before, is that if you want to study a phenomenon, if you have to perform a manual identification, the only things you can handle are scalars or curves, okay? So to do that, it's interesting to use a representative volume element, okay? This is due to Buffon. Buffon was the first one to say that you have to have a sort of specimen that average the different the microstructure, in fact. He was studying wood pieces. Or you can have a very well-known heterogeneity, like in bending, in elastic bending. But otherwise, you've got heterogeneities and you can say nothing about your experiment results. This way, for this reason, people start to look for very homogeneous gauge zone. So for that, they find the solutions that I call the comfortable Saint-Venant principle. This is the idea that if you use a very long specimen, the gauge zone is far away from your boundary condition, and everyone here knows that in this case, well, if your boundary conditions are not perfect, usually in the gauge zone it's nearly perfect. There is a safe alignment of your specimen, so you know that, for example, you've got something that has nearly pure tension, and in that case you can deduce the stress directly from the geometry in the elastic case, and you can measure the strain with different measurement devices or techniques like grip displacement, extensometer, strain gauges, and of course full field measurement nowadays. So this is the easy way, but it takes us sometimes to only achieve this type of normalized specimens. Ah oui, bon, okay. Alors, okay, bon. So the thing is that if you start to study complex behavior like anisotropy, well, having just a long specimen is not the good idea. So, for example, Böhler proved that clearly just having joints at your clamping system, in the clamping system, is important because you have a more homogeneous strain than before. So this is the first improvement of the technique. A second problem is if you are performing biaxial test, even with isotropic material, the gauge zone sides are not Neumann boundary conditions, so you constrain the Poisson effect. So the idea is to add slits around the gauge zone. This allow a free expansion or contraction of your gauge zone, and you have much better results because you are much more homogeneous. In the case of anisotropic material in biaxial tests, you've got still this problem. This is the shear stress heterogeneity if you have no slits. This is just with slits, so you see that it's much better. But if you also add hinges, so you allow rotation of the ends of your specimens, you have something that is even more homogeneous. Well, sometimes it's not possible to have something that is homogeneous because it is a structure because of, well, technical limitation. But what you can do at least is a small but existing compensation. It's to measure the boundary condition, to measure it with full field measurement, and to measure the static values, as you said before. For example, with 6-axis load cells, 6-axis load cell, you can made them by yourself. It's not very complex, it takes some time, and you can buy them. It's not very costly. I mean, it's just a little higher than a regular one, and it's the same size, so you can use it very easily. But strangely, very few people use that. Perhaps because you will see that your numerical results are far from what measures a load cell. It's just guessing, I don't know. So, to put it in a nutshell, for isotropic material and long spectrum, it's very easy. Infinite principle is sufficient. But for anisotropic materials, complex behavior, short specimen, well, you must start to really choose very accurately your boundary condition. You can have an independent choice of the different degrees of freedom of your boundary condition, like free rotation or not. You can measure the displacement or the force components, and finally you can even adjust your boundary condition at the beginning of your test, or even have a sort of live compensation. But this is very rare because you will need several actuators that will compensate during the test. So it's a very high price. So what is done with the generalized continuum mechanics test? There is one special case I just want to show because it's very different from the boundary, I would say, boundary condition regular test, but which is quite beautiful. It's based on the idea of the size variation approach. It's quite an old approach proposed by, I think, Lakes in '86. The idea is that you use a specimen, you measure its stiffness, and then you reduce its thickness by machining, polishing, rounding it. But it's the same specimen, so it's very, very long. It's a really tedious work because you have to take it, measure it, machine it, then measure it again, and so and so. And you've got...
Are you sure that machining it, you are not changing it?
Yes, he's saying that it's a real problem. You have to be very careful with the condition of machining, grounding, and polishing. Of course, you're right. Especially because with a very small size, you start to tackle with the internal length scale, and of course you can degrade the length scale because of the machining. Exactly. So there is a very highly delicate setup that he is using. Like the specimen is the red part here, is just clamped in the upper part, and there you've got two solenoids with magnets, and you can perform torsion and bending without friction. It's really beautiful. You use interferometry to measure very small displacement, and that way, after I don't know how many days of measurements, you've got these curves, and you show that you've got not a linear variation of the stiffness with the square of the power 3 or 4 of the thickness of your specimen. But this is a very special case, but at least it was interesting to show you because it's quite amazing. So, if you want to apply boundary condition and perform a test, a shear test, tensile test, or whatever, what can you do? Usually you can choose between what I would say uniform, that is to say rigid body motion displacement of the upper part or the sides or lower parts, or a uniform Neumann, that is to say homogeneous force applied there or there or there or there. Well, in this case, this one is very easy to do. I mean, you're just clamping everywhere. But in fact, you can only apply shear this way. And it's very constrained. I mean, if there is a proper known, a specific kinematic that want to develop, it is stuck by the clamping around the specimen. On the contrary, if you are using uniform Neumann boundary condition, you can perform tension, shear, and it's unconstrained. So you will see much more displacement. So it's interesting for full-field measurements. What people were doing for standard continuum mechanics were usually uniform heterogeneous boundary condition, free sides and clamped hands. Okay, so you've got Neumann and Dirichlet there. What can be done? It you can also do other things, because this is easy, you can perform tension and shear, but if you want to look at something more complex, it could be interesting to change a little bit this boundary condition. So you can decide to have an inner Dirichlet boundary condition or an inner Neumann boundary condition. How to do that? Well, in the case of Neumann inner boundary condition, it's very easy. It's just a crack or just a hole. So you just have to drill a hole in your specimen and you will have an intense gradient appearing inside the specimen. So it could be interesting. Well, having an inner Dirichlet boundary condition is quite difficult. But once more, you can have an intense gradient. You could change your mind and have mixed degrees of freedom on the boundary. Like here you can imagine you could have an imposed displacement in one direction but free expansion in the other. That was the previous idea with slits. And this is quite hard to perform, but you can manage. And the interest is that you control more the homogeneity or the degrees of freedom you want to tackle. You can also imagine that instead of having heterogeneous boundary condition, you have very singular one, like just applying a displacement at a node, especially. It could be interesting. It's not very complex, and the interest is that you induce an important gradient which could be really dedicated to the model you're studying. And last, you can even say, but well, I can still use Dirichlet or Neumann boundary condition, but no longer uniform. It could be high order, like I don't know, a sine, a power law, so that you will have important gradient appearing close to the boundary condition. But this is quite hard to do. And even for the Neumann, it's even harder. But once more, it's unconstrained for Neumann boundary condition. So now some examples of all these applications very quickly. First idea, global tension displacement. It's a very well-known bias extension test. It's well known for fabrics and for pantographic structures. It is interesting because it's working well, because you've got a sort of RVE there. And you can clearly see compare different models with that. The energy are clearly different with such type of boundary condition, so it is quite interesting. You can perform shear. The same thing as before. It's quite easy to perform them. It's working well because you can differentiate quite well the different models on such type of tests. You can perform torsion. It's out of plane, of course, but it is still interesting. In a recent paper, it was shown that you even have an inversion of the pointing effect during torsion. That is, say, the axial force induced by torsion is inversed during the motion, during the imposed deformation, with quite easy boundary condition, I would say. Here you've got a complete Dirichlet boundary condition. It's a pure shear test that was done. And
you have this machine?
We don't. This is by Lonen. And it's a special one because here you've got load cells there to control the initial and during the test.
It's difficult to make this?
Sorry?
It's difficult.
I think it's not that difficult, but as any experimental part, I mean, the designing, the machining of the setup and all that stuff, it takes some months, yes. And then tuning everything, it's some months. So I won't say it's that easy. It's not complex, but well, it takes some months to do that. Especially here, it's very clever because you have load cells that measure the biaxial tension, initial one, and then the evolution of the biaxial tension during the shearing. And so you've got also an initial adjustment of the initial tension, and you can see that during the test, depending on the initial tension, the behavior change. I mean, not the behavior, but the response change. So this type of measurement is really interesting. You could have inner homogeneous Neumann. What I said before is you could have a crack there. So this is an artificial crack, you just cut your specimen. You can't see it there, but it's a hexagonal pattern. And you've got Dirichlet boundary condition there, you've got Neumann there, and you've got a crack, so an inner Neumann. This is a beautiful work done by Rettori et al. In 2015. They managed to identify strain gradient model. You see here the different material parameters they have identified with such type of test. So it's possible to do that. I mean, this was done already with standard continuum mechanics, but here it's really interesting because you are tackling characteristic lengths with such a high gradient. Ouais, je suis à la fin. You could have uniform Neumann boundary condition. This is very rare, in fact, even for standard continuum mechanics, because it's difficult to apply. The only reference I know of that was done at the end of the 70s and related and reference in the 80s, and then we have done that on a centrosymmetric and non-centrosymmetric pattern to see that the Cauchy elasticity was not able to predict such type of sort of bending induced by uniform tension. You've got what I would call singular Dirichlet boundary condition, like this is the well-known fiber pull-out test. So you just are pulling out a fiber of your pantographic structure, for example, and you can see if your model is matching quite well or not here. And one of the last is what I call the high order Dirichlet boundary condition. Here the boundary condition applied are more or less sinus. You see here this is a displacement of your upper and lower boundary condition, and you see that you see the transition from the information from there to the inner core, which is nearly homogeneous in fact. And last and not least, because I think it's in the spirit of what I wanted to say, this test that, well, the author says it's a failure, but it's a failure, but the idea is beautiful. I mean, this is what I call I know there's a name, the name they decided for that, but a comb test. You've got two combs, okay, with tooth there, okay, the teeth are there, okay. One here, 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 one here, 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 here. And you've got a sort of pantographic structure, and then you are applying uniform tension. And instead of measuring the strain, the displacement between the two combs, you are measuring the displacement out of this zone. This is very clever. I mean, this is the spirit of choosing your boundary condition, because with Exactly, and thank you for that. I mean, this is a beautiful idea. I mean, you cannot think of that if you are studying standard continuum mechanics, because it has no sense, okay? So this is a really interesting idea, even if, well, at the end it was not working for technical reasons. At least the idea is in the spirit of my talk. So to summarize that, there were just some examples. I mean, you've got thousands of different types of tests. Most of these tests are or may use easily fulfilled measurement, and we must use fulfilled measurement because it's a modern way to do that. Well, you will lose so many things if you are not using these techniques. What we must remember is that for standard continuum mechanics tests, there were decades of evolution. In the end, the standard boundary conditions are quite simple, but you've got some very complex cases that I show you that even emerged in the 90s. And for the generalized continuum mechanics test, well, in fact, it's still very young. It's a few years, decades, we are starting to study in an experimental way such materials. So in some cases we can use identical tests, tests that are identical to standard continuum mechanics ones, and it's relevant, but sometimes perhaps it's interesting to change. So we have to study that, because sometimes dedicated one could be really interesting. Well, so I will end with just stating the obvious. We must not forget to choose our boundary condition, because is they depend on the sort of behavior, and in the case of complex behavior, perhaps the regular boundary conditions are not the good one. That's all. Thank you.
Thank you, Martin, for keeping in time. Unexpectedly.
Yes.
I'm sure there are many questions.
You didn't say much about miniature testing. All your specimens.
Sorry?
Miniature.
Oh, yeah.
All your specimens which you showed
Are large.
big.
Yeah.
So there you still have a chance to control, to some degree, your boundaries.
Yeah.
But what do you do if you have something really small? You just...
Yeah. You're totally right. At small scale, it's really difficult.
You simulate it.
Yeah, usually simulated.
Theory, you simulated and you...
Usually, I mean, you don't need perfect boundary condition, but the idea is, once more, you have to induce a reaction of your material. So perhaps it's a little bit nasty, your boundary condition, but it's inducing something. So if you measure your boundary condition, and it is well chosen, well, you can compare, you can perform FIMU or whatever you want. But the thing is that, of course, having perfect boundary condition is an illusion, especially at small scale. It's clearly not possible. However, at small scale, you can have very clever setups that are directly engraved on, a wafer or something like this.
Yes.
You have people that
Do that with certain materials like silicon.
exactly.
But if you have just some plastic, some polymer,
Oh yeah,
everyone is an individual. So this is
exactly.
And just for my clarification, because I always have problems with this mathematical terminology. So when you say directly, you mean
Displacement.
Displacement control.
Yeah.
And when you mean Neumann, you mean force control.
Force or or stress or but well.
Why are we saying this? Just to have this link to the theoreticians?
Because usually people say that way. So usually people will say it's because usually people are doing numerical simulation and they call it that way, and so it's quite funny to say, well, from an experimental point of view, I say displacement, but it will be translated into directly in a publication. So it had some confusion. At the same time, it's tricky to say, well, we are talking about the same thing, but not exactly. So it could be interesting, because usually people will say, oh, you just apply a force. Well, in fact, it's just an average force, because it's clamped, in fact. So it's an imposed displacement, and I have just an average value of the force. So all the trick is to know how to translate the real boundary condition into the numerical simulation.
Okay. Next question.
Yes, Pierre.
If you are suspecting a strain gradient material, then you have to make a difference between directly boundary condition and clumped boundary conditions. In the sense that you fix the displacement, but you can also fix the normal derivative of the displacement.
Yes, and this is one of the technical limitations I was just quoting. I mean, it's very difficult if you are studying such type of materials, because you want to hold them, and at the same time, if you want to hold them, you will clamp them, so you will delete some degrees of freedom. So you have to really think about how to just have a contact. It's very complex. Yes.
Almost the same question. So how to apply a normal gradient? So how to apply some displacement onto a layer a little bit inside?
I mean, this is perhaps the best idea. I mean, if your two combs are very close together, it's a sort of layer where you are applying a strain. I mean, I would say that.
I think most people did not understand.
Yeah. It's. I'm sorry. The gray level images. You've got one tooth there, one tooth there, one tooth there, one tooth there, and one tooth there. They are related to a solid, so you've got a global displacement there in this direction, okay? And here you've got a second series of teeth that are going in the opposite direction. So you are applying more or less a uniform strain there. And the genius there is to measure the displacement out of the in-between part. I mean, this is not interesting. The interesting part is there because you will have a strain if it's a strain gradient model.
It's almost in the middle of the set.
But yeah, why not? You can even imagine that these teeth there are close to the other one. It could be exactly the same. I mean, you just take this comb and put it there, and you've got your two combs very close together, and you've got free ends everywhere except there where you apply a strain. And you will see the strain spreading to the left.
I propose that you continue the discussion at the coffee after the next presentation. So let's thank again